So hello, welcome to our exam 3 visual slide. Here's chapter 16 in the table of contents. So the first one is classify dienes as conjugated, isolated, or cumulated. A common misconception is isolated means no double bonds. Current belief, double bonds separated from another double bond more than one carbon away. What I've learned, conjugated double bonds are separated by one carbon. Isolated are double bonds separated by more than one bond. And cumulated are double bonds right next to each other. So which is conjugated? The correct one is the one that's highlighted with correct because they're no more than one carbon apart, and the incorrect one is actually cumulated. So rank the stabilities of various dienes, cis versus trans. The misconception is S-cis is more stable because the double bonds are closer. The current belief is S-trans is more stable because of less steric hindrance. What I learned is S-cis takes more energy than S-trans. Which is more stable? The one highlighted in blue is more stable because it's further apart, which is less sterically hindered, and that is also S-trans. So draw the resonance structures of allelic cations. Allelic cations is the 1,2 is for 1,2 product, and the current belief is allelic cations is for the 1,4 product. What I've learned is if the starting material is symmetrical, then two products in which the 1,4 needs the allelic cation resonance before final product. And so which is the next step, A or B for the resonance of the allelic cation? And the correct answer is A because that leads to the resonance form, where B leads to the 1,2 product. Explain the role of temperature planes in determining if kinetic or thermodynamic product is formed. Misconception, high temperatures yield the kinetic product. Current belief, high temperatures yield the more stable product, thus are more thermodynamically favored. What I learned, higher temperatures induce a more stable product and thus longer to form. Conversely, lower temperatures favor the kinetic product, which are less stable and takes less time to form. So as you can see here, the second reaction is correct because the 1,4 product is the major product when in lower temperatures versus the one up top. Showing the correct stereochemistry of the product of diols-Alder reaction. Misconception, trans and cis dienophiles have no impact on stereochemistry of the final diols-Alder reaction. Current belief, cis dienophiles have a specific stereochemistry and are normally placed on the same side when drawing the product. The same rule is applied to trans dienophiles. What I've learned, cis dienophiles have the same substituent on the same side, while trans dienophiles have the substituent on opposite sides. Which is correct? Which is the correct stereochemistry? So the correct one is A because our dienophile is trans, so our conformation should be trans, so the other one is cis. So now we're on chapter 17, and this is the chapter 17 table of contents. And so here we determine the Huckel's rule applies to a given structure. Misconception, compounds can only be either aromatic or anti-aromatic. Current belief, compounds can be non-aromatic. Determining whether a structure is aromatic, non-aromatic, or anti-aromatic depends on the hybridization of the compound as well as the number of pi electrons pairs. What I learned, when determining if a compound is aromatic, non-aromatic, or anti-aromatic, you must use Huckel's rule. If the compound has an odd number of electron pairs, it is aromatic, and if there is an even number of electron pairs, then the compound is anti-aromatic. In order for a compound to be non-aromatic, the compound does not have a fully conjugated ring with overlapping p orbitals. So this is the difference between the aromatic and non-aromatic. The compound is non-aromatic even though there are 3 pi electron pairs, contributing to the compound's ability to be aromatic. However, in order for the compound to be aromatic, the compound must meet Huckel's rule and have a full conjugated ring with overlapping p orbitals. In the compound, the hybridization of the carbon located at the top pink dot is sp3. Therefore, the compound cannot be aromatic. For heterocycles containing nitrogen, predict whether the nitrogen atom is strongly or weakly basic. Misconception: you do not need to know if the lone pair is necessary for aromaticity. Current belief: knowing the pKa and if the lone pair is used for the aromaticity makes finding if the nitrogen is strongly or weakly basic easier. Well, I've learned if the lone pair is necessary for aromaticity, then the lone pair will be more on the weakly basic side. So here, the first one is correct. Weakly basic. The nitrogen is weakly basic because its lone pair is necessary for the aromaticity, where the other one cannot contribute to the aromaticity, so it is strongly basic, which is wrong. Name benzene derivatives when given the structure. Misconception: there is only one way to count the carbons in the benzene ring. Current belief: it is easier to use the common names chart to determine the parent names. What I've learned: benzene derivatives can have more than one name depending on which way the carbon in the benzene ring are counted. So the first one is correct: 2-methyl-1,3,5 trinitrobenzene. This is correct because when naming comes before T, also the numbers are placed in numerical order. The second one is incorrect because 3,5,1 trinitro 2-methylbenzene. This is incorrect because the numbers are not numerical order and the words are not in alphabetical order. Draw benzene derivatives when given the name. One misconception is that when you draw a benzene derivative, you can just put the substituent anywhere. Current belief: when given the name, it tells you the location of the substituents. What I've learned: when drawing the compound, it is best to draw the parent chain first and then add the substituents. So draw the structure of 1-bromo, 3-nitro, 5-chlorobenzene, and the benzene is the parent chain. The compound on the right is the correct structure. In the structure, the substituents are placed on the correct carbons as given in the name. The structure on the left is incorrect because the substituents are in the wrong place. So here's the Chapter 17 reflection. In Chapter 17, we learn many things. We learn how to determine if a compound was aromatic, anti-aromatic, non-aromatic through the use of the Huckel's rule. To be aromatic, the number of pi electrons must be odd. For an anti-aromatic, it must be even. Hybridization must also be taken into account. When we also learn how to name benzene derivatives as well as draw the structures when given the name. We also learn the effect nitrogen has on aromaticity and how lone pairs as well as charges affect this. Chapter 18. Hey, here you go, Makita.
Okay, so Chapter 18, we have the Chapter 18 table of contents. To begin with, we have the halogenation of benzene, bromination, and chlorination. A misconception about this is the deprotonation occurs first, taking a proton from the aromatic ring and creating a carbocation. The current belief is the nucleophilic attaching the Br/Cl to the same carbon as the proton, creating a carbocation. And I've learned that during halogenation, nucleophilic attack occurs first, attaching the Br/Cl and creates a carbocation. The carbocation goes through resonance or sigma complex. Then the Br deprotonates the carbon and the pair of electrons form a double bond, completing the aromatic ring. Nitration of benzene, mechanism starting with nitronium ion. Misconception about this is the deprotonation occurs first with the O and the nitronium ion creating a carbocation. The current belief is the nucleophilic attack occurs first with the OH, with the deprotonation of sulfuric acid by NO3. And I've learned that the nitronium ion is formed first. Sulfonation of benzene, mechanism starting with SO3. Misconception is a nucleophilic attack will occur. What happened at one of the oxygens? The current belief is the aromatic ring, which is the nucleophile, will attack the sulfur, and the bond between it and the oxygen will break. I've learned that the entire SO3 atom is being attached to the ring from the sulfur and not just the oxygen atom. So the reaction at the top is incorrect, because instead of attacking the sulfur, it's attacking the oxygen, and the oxygen is being connected, which leads to there not being a negative oxygen which is supposed to be there. And yep. Friedel-Crafts alkylation. The misconception about this is the carbocation in the alkyl group stays in the primary position. The current belief is the carbocation moves to the most stable position, and I've learned that if Cl is the primary position, the carbocation will move to the secondary position where it would connect to the benzene ring. Friedel-Crafts acylation. A misconception about this is the only way for acetylene ions to be resonance stabilized is the rearrangement of them, is to rearrange them. The current belief is acetylene ions do not undergo carbocation rearrangement. What I've learned is if an acetylene ion were to undergo carbocation rearrangement, the stability from the full octet would be lost. Therefore, acetylene ions do not rearrange. The mechanism for acylation is similar to alkylation, but not the same. So, for the top reaction is the wrong mechanism, and the bottom is the correct one. We have the acid chloride in the rearrangement for the correct one instead of the RCl, and the AlCl3 being our catalyst, but the RX is not an alkyl halide. Next, we have oxidation. The misconception about this is all benzylic compounds can undergo oxidation, but the current belief now is all benzylic compounds cannot undergo oxidation. I've learned that in order for benzylic oxidation to occur, the benzylic carbon must have at least one CH bond or one proton. Does the reaction occur in the problem below? For this problem, the reaction does not occur. The reaction does not occur because, as we see at the benzylic carbon, it does not have an H or a proton attached to it because it is connected to 4 other carbon groups, and there's no room for the hydrogen to be placed. Next, we have benzylic bromination. Misconception about this is benzylic bromides can only undergo an SN1 substitution. Another misconception is that the bromine ion can be added to any carbon after the reaction takes place. The current belief is benzylic bromides can undergo both SN1 reactions and SN2 reactions, and bromine ions can only be added on the benzylic carbon. I've learned while benzylic bromides can undergo SN1 substitution, they can also undergo SN2 reactions when the benzylic bromides are unhindered. So for our reaction at the top, it is the correct one because the bromine was attached to the benzylic carbon indicated at the blue dot, and the benzylic carbon is the carbon directly attached to the benzene ring. Next is the reduction of ketones, Clemmensen reduction. The misconception about this is the Clemmensen reduction replaces the carbonyl group with a lone hydrogen atom. The current belief is the Clemmensen reductions reduce the carbonyl and then replaces that group with 2 hydrogen atoms. I've learned that a methylene group is used in Clemmensen reductions, which is CH2, which is where the two hydrogen atoms are obtained. So we have a correct mechanism, which shows the mechanisms and how there are two hydrogens that are obtained through and used through the Clemmensen reductions. Next we have nucleophilic aromatic substitution. If a misconception about this is if H3O is used in the reagents, it will be an elimination addition mechanism. A current belief is if a stronger reagent is used or if there is a very high temperature, elimination addition will occur when there is a weak electron withdrawing group. What I've learned is that elimination addition does not occur if there are no strong electron withdrawing groups in the ring, so a strong reagent or high temperature is used to make it occur. In the reaction on top, the NO2 is a strong electron withdrawing group, so it will go through an addition elimination reaction. While for our bottom reaction, there's a Cl, and that is a very weak electron withdrawing group. So we will add a strong reagent, which in this case is the NH2 for the NaNH2. Next, we have how substituents on the aromatic ring promote substitution at some positions but not at others. A misconception about this is two different products will be obtained, one for each substituent, but my current belief is the stronger substituent group will dominate the directing effects. And I've learned that substituents that are closer to the strong activated end of the spectrum would be the directing group over the substituents closer to the strong deactivators end. So in our reaction at top, it is incorrect because the Cl is being directed ortho to both the methyl group and the O group, but in the ester group. But the bottom one is the correct product because the Cl group will only direct to the ester group because it is a stronger activator than the methyl group.
And this concludes our exam 3 summary.
That's all.